Hello, hello, and welcome to this Inspire edition. Dear girls, dear boys, I'm the director of the Inspire 2021, together with Susanna Bertelli. I'll show her photo in a minute. And I'd like to welcome you to this edition. Of course, we would have liked very much to have you here, because usually this school, this Inspire school, was in presence. It's a pity not to host you here, but I hope you will enjoy this edition. Even if you are not here physically with us, you are here, let's say, mentally with us. So let me show you something and tell you some words about this edition. Usually we are dedicating each year our school to some peculiar item. And this year, as you all know by now, of course, we decided to dedicate this edition to the magic realm of the particle accelerators. Because accelerators are everywhere. They are, of course, in the physics labs to study physics beyond the physics we know today, and we will hear shortly about this in the very first talk of this edition. But they are also used to make some research in real life, so like uh, art and culture. There is a very important accelerator, the biggest out of all, namely the universe, and we will hear all this in this edition. So, as you know, maybe you have seen this already. So this is a fully online edition. Unfortunately, we would have liked to have you here. And it will run each day until Friday included, from 3 to 6. This is the Rome time, so Italy time, hosting a series of lectures, but not only. We will also have visits to our own infrastructure here in Frascati Lab, and we will also have one of the talks which will bring us in a lab, which is the CERN laboratory, the biggest lab in the world. We will have an interactive lecture which will show us how the things are going there. So it's as if we bring you with us there. This is a very nice picture from our laboratory, which is centered on an accelerator. Actually, here in Frascati, the technique of colliders was born. So for the first time in the world, we have developed here many years ago, by the end of 50s, early 60s, this technique, which is collisions of beams of particles. And here you see actually the building, which you will see it better in the virtual tour, which we are doing on Wednesday. That's a picture from outside. That's the Daphne Collider. That's instead a picture from inside. And that's one of the reasons which pushed us to organize this edition and to bring you into the magic realm of accelerators, just because we are expert in accelerators in their use as well. And accelerators are fascinating and very peculiar machines, as you may imagine by looking at this picture. That's a photo which we took 2 years ago, so was Inspire 2019, where we hosted you, I mean, not you, but your colleagues who were here with us that year, nearly 100 persons as this year. So we opened the registration to you. Of course, we will post our videos online, but only 1 week after, because we want to give you the opportunity to ask questions, and you can ask questions by writing them, and we will answer them. So we want to treat you in a privileged way, even if you are not here with us. Usually we were doing experiments and hands-on experiments with participants. We were hoping last year, when we were pushed to organize very fast an online edition, that this year will be possible to have you here. Unfortunately, it's not yet like this, but as I was saying, you are participants coming from many countries, actually from 55 high schools and colleges from all these countries. Actually, this morning we hit 100 participants, which are coming from, you see all these countries: Albania, Bangladesh, Egypt, France, Germany, Italy, Pakistan, Romania, Slovakia, Spain, and USA. By the way, the first thing I'd like you to write to us in the chat is, where are you coming from? So just to send us a greeting and tell us your name and your country and your high school. We would be very happy to learn whom you are by writing to us. And as you have seen, our program, it's centered on accelerators, but not only accelerators. We will have a virtual tour on Wednesday, where we will bring you in our DAFNE accelerator, but also in our visitor center, which is hosting a series of experiments and techniques which we are using. And a part of this, you see here, we have a talk which is not related to its accelerator, but it's something else. It's quantum universe. So something about the quantum physics. Then we have something about the antimatter. So antimatter, which is produced somehow in accelerators, and we will learn about antimatter, which is again very, very fascinating. And we have, as I was telling you, something about the most important and the strongest accelerator out of all, namely universe itself, under space accelerators. So once again, I welcome you to this 2021 edition dedicated to accelerator. And you see here our program once again. This edition, it's sponsored by and it's organized with the support of these programs. One, it's a program which is dedicated to test on quantum mechanics, so testing the large-scale limits of quantum mechanics. The other one, Foundational Question Institute from United States, which is financing projects answering to questions about the universe. And the third one, an European program, Strong 2020, which is actually financing research in many of the fields you are going to hear during this edition. What is the strong interaction, and how can we study the strong interaction by the use of accelerators? And last but not least, I'd like to show you whom we are, because that's, of course, not only me. Together with me, we have my co-director, Susanna Bertelli, whom you will see again as a chair in one of the next days, but also our beautiful team of educational and dissemination of science. You see here Sara Reda and Elisa Santinelli. Here it's Elena Patrianelli and Sara Arnone, last but not least, Deborah Bifaretti, whom you are not seeing right now, but they are there and they are taking care that everything works very, very fine. Having said this, I welcome to you once again to the 2021 edition of this school. And please write us a greeting in the chat, whom you are, where are you coming from. And with this, I open to the first lecture. You see the very first lecture, it's given by Sergio Bertolucci, who will join me right now. He is, well, his CV, if I would start reading his CV, I would take all hour just to read his achievements, because he was director of Frascati National Laboratory, then he was in the chairing board of the INFN, the vice president, and then he was director of research at CERN itself. Now he's at the University of Bologna, pushing forward new research in the field of neutrinos and also in the field of applications of physics for the real life. And who better than him could tell us something of the evolution of the accelerator and bring us into the magic of the accelerators from the very beginning, namely the cathode ray tubes, to the LHC, where he was the director of research. So we will hear a journey into the electron accelerator up to the Higgs boson. So with this, I welcome once again Sergio. I thank you for being here. Oh, wow, I didn't see, but I see now many greetings. Oh, wow, yeah, I'm so happy to see you. So welcome France, welcome Bergamo, welcome Sora, welcome, welcome everybody, welcome Romania, welcome people from all this beautiful country, and it's nice to have you here. I will greet you once again later on. So we are organized as follows. I will leave the floor to Sergio Bertolucci, to whom I thank very much for taking his time to be here with us today. We will have questions and answers, 20 minutes at the end. But if you feel like wanting to ask something, an urgent question, just do so in the comments, and I'll stop Sergio and ask your questions as up, so you don't feel like being too late to get an answer. So once again, hello to everybody. It's a pleasure having you here. Sergio, I leave the floor to you, and please bring us into the magic of accelerators. Thank you very much.
Thank you, Catalina. After your presentation, I can only disappoint the audience. Can you see my slides, first of all?
Yes, Sergio, we see very well your slides. You are perfect.
So anyway, let's try just to do this very fast, and I hope not to confusing trip into the accelerator and their implication is sort of archaeology of accelerator from the beginning up to nowadays. And accelerators are extremely diffuse worldwide. They can vary in size from very small meters to tens of kilometers. The biggest one now is the LHC, is 27 kilometers. And people are designing the next one, which will be 100 kilometers at least. It can cost from 1,000 euros or dollars to billions. And sometimes, in order just to build them, it requires a lot of time, a lot of money, a lot of people. Why are we doing that? And why is worth the challenge? The challenge is worth because accelerators are a beautiful instrument, is sort of a Swiss knife for doing not only fundamental research in particle physics, but also just to investigate the same question that cosmology is investigating, for making a beautiful instrument like light sources, extremely brilliant light sources, which can allow us just to investigate and look at proteins, at viruses, at the structure of matter. They can be used for medical application, for industrial application, and even just to make ourselves more secure. Why we need accelerators, all in all? I tell you a story that you probably know, but the answer comes from the basic principle of quantum mechanics. If you want just to see something, you have just to illuminate this something and let the scattered wave get to your detector, which usually is your eye, is one of the most sophisticated detectors. And there is a limit in which you can distinguish the feature of the things. For instance, if you want just to see, you make a hole in a dark foil, and then you have a source of light, you will see on the other side on the screen that you have a diffraction figure. So you will be intervals of light, dark, light, and so on. And if you put something inside this hole, how small you can tell that there is something inside this hole. And you know from the fundamental optics that essentially you can see things as long as they're bigger than the wavelength that you're using for doing that. So essentially, if you're using visible light, and even if you're making the most sophisticated microscope, you'll never be able just to see things which are below, let's say, 0.2, 0.3 microns. Now let's make another thing. Let's make two holes. And of course, if you plug one of these holes, you'll see the diffraction figure. If you leave the two holes open, you see an interference figure. You'll see things which are not only the simple set of round spots, dark and clear, but you see a pattern which will be more sophisticated, because the two waves, we know that light is a wave, will interfere, the wave will interfere coming from the two holes and will give a more sophisticated pattern. Now, there is a problem, is that in about 100 years ago, Albert Einstein postulated and discovered, gave a very good explanation for photoelectric effect. Say, well, light is, you can consider light a wave, but you can consider it done by particles, by photons. He invented the photon. He got the Nobel Prize for that. He didn't get it for relativity, he got it for the photoelectric effect. And so photons are particles, and he did it just to explain something that people could not understand, is that if you were putting light, very intense light, on a piece of metal, sometimes, regardless of how strong the light was, you could not extract electron by photoelectric effect. You needed just to have a wavelength which was shorter than a certain number, which was the extraction potential, we understood later. And this was absolutely needed, because otherwise, regardless of the intensity of light, you were not extracting electrons. So photons, light, is made by photons, by particles. Now there is a problem. There is a problem which is a well-known problem in quantum mechanics, is that if you put the same light, which now is, you know that you can consider also done by photons, through these two holes, and you can send it one photon at the time, so very feeble light, you still see an interference light, interference pattern. So you count, and you see that the number of times you hit the center of this figure is bigger than the number of times in which you hit where there is clear, and so on. So where the hell this photon goes? And in the moment you want just to know where it goes, the figure disappears. So a photon is a particle and is a wave. And you cannot distinguish these two aspects. It is a duality which is all embedded in quantum mechanics. And this applies not only to photons, it applies to particles as well. So a particle is, you can consider a particle also as a wave. And its wavelength, the Broglie wavelength of this particle, is essentially given by a very small number, which is the Planck constant, divided by the momentum, the particle momentum. And this hypothesis, which was one of the cornerstone of quantum mechanics, was confirmed already in 1927 by looking at the diffraction pattern in crystals, which have a very small space between the different atoms. And so you can scatter electrons on that, and they were behaving exactly like the photons. So now you start understanding why we are using accelerator, because the accelerator are a very efficient way just to make very short wavelength, which means that we can probe the matter, the things at a very small scale. For instance, if you get a very low energy for an accelerator electrons, which has 1 keV, 1000 electron volt energy, its wavelength is 30 times better than what you can do with visible light. And this, for instance, gives you the possibility just to make very sophisticated and very high resolution electron microscope. So just to put it in I think if with optical microscope, which are using visible light, you can get up to 10 to the minus 4 centimeter. With electron microscope, you gain at least 3 orders of magnitude. With radioactive sources, because they're using a particle which have higher momenta, you can go to 10 to the minus 12 centimeter. And with accelerator, you can go up to 10 to the minus 17 centimeter, which, if you think, is a very small number. Now, let's now say once forever some units. The units that we use in accelerator is the electron volt. Of course, we are using many of them. We are using million electron volt, trillion electron volt, tera electron volt, which means 1,000 billion electron volt. And an electron volt is the energy that a particle at rest gets after it is accelerated with its unitary charge is accelerated by 1 volt electrostatic potential. So essentially, even at LHC, if you translate it in Joule, you see that 7 TeV is essentially a small number in itself. But if you imagine that this energy, 1.1 10 to the minus 6 joule, is brought by a particle which has a mass which is infinitesimally small, you have just to compare. This is more or less the energy of a mosquito, and which is flying around. But if you can imagine several tens of billions of mosquitoes, you can understand that the energy that you store in this machine is big. Accelerator, for this, they use also another thing that we have learned through relativity, is that energy and mass are two currency of the same object. So they are connected with the famous equation that you see up in the screen. So essentially, if you can, if you use the energy of beams against a target or a beam against another beam, you will be able just to transform in the energy in mass of other particles which are not existing before. And for instance, in this way, you can reproduce particles which are no longer abundant in our world because they have disappeared long ago, or they are less frequent in our normal life. Another thing that accelerators are fascinating for is that since when you are clashing beams of particles one against the other, in the place where you have this interaction, the density of energy, the temperature, if you like, which is the same, is so high that it's like the density, the average density of the universe when it was very, very young. And so essentially in a small volume and for a tiny amount of time, you are recreating the same situation which was at the beginning of the universe. And the higher is the energy that you can put in this micro sphere, the closer you go to the beginning of the universe. In this moment, with the highest energy that we have achieved in accelerator, we can study the universe, the condition of, we can reproduce the condition of the young universe when it was 1/1,000,000 of a millionth of a second after the Big Bang. Accelerator are used also for other things. If you get a particle and you have it circulate in a circle, this particle, especially if it is light, like an electron, will essentially emit radiation in a short pencil around the orbit. And this radiation will be of higher energy, usually goes in the X-rays or above. The more energy you have in the beam, and the more strongly you focus, you bend this beam, the more you have the energy and the brilliance of the amount of photons you are setting out. And modern light sources are fantastic object to study matter at the scale, which, for instance, is very interesting for material science, for biology, and for structural analysis. For instance, this is a picture taken. If you look at the scale in the bottom part here, you see that this thing is 5 micrometers, and you see the feature, which you see the spore here. And we can do even better, because we can do now sources which are essentially laser in X-rays, which have an enormous brilliance. So the number of photons per unit surface is very high. But not only, these photons are all in phase. So in principle, you can get this light hit a single cell, and before this cell is destroyed, you can take a hologram, a 3D picture of that. And this, for instance, will allow just to study all the proteins, all the viruses, which are otherwise almost impossible to study elsewhere. And this is, for instance, the reconstruction of a cell structure done some time ago in one of these free electron lasers in Germany. Accelerator can be used also to cure cancer, or just to make diagnosis. Accelerator X-ray tubes are accelerators. The electron linac, which are used in the hospitals for curing, treating some type of cancer, are accelerator, a linear accelerator. Lately, in Italy is one of them, which was built with the help of the Frascati lab and of INFN. There is a machine which accelerates protons, which can destroy tumor cell while doing less damage to the healthy cell. And this place, there are a few of them, there are several of them in the world, and one of them is in Italy, in Pavia. Accelerators are used in countless other applications, which goes from material science to industrial processes, like, for instance, sterilization, to homeland security, just to find people who smuggle dangerous things inside the transportation. And just to give you an idea of the number, there are in this moment more than 25,000 accelerators in the world, and less than 1% of these accelerators are used for research, for fundamental research. The rest are used for doing essentially industrial research, medicine, medical radioisotope, and ion implanting, which is very important for making all the semiconductor objects that are inside our cellular phone. And essentially, accelerating particle is the way in which, as if you remember this famous relation of the wavelength, in which you make shorter and shorter wavelength, and so you can look at the matter closer and closer. And in order to accelerate the particle, you have just to give them a kick, a number of kicks, and the force that you can apply to first of all, the particle that you accelerate should be charged. Otherwise, the only way in which you can do this acceleration is just to take a charged particle, get it against a place where there are a lot of neutral particles in such a way that some of your high speed charged particle will kick the neutral particle, and this is called spallation. And for instance, is how you make very strong neutron, which are neutral particle beams for again making different studies in nuclear physics and in applied science. So, as you know from the Maxwell equation, the force that you can exert on charged particle is essentially the electrical force and the magnetic force. But you cannot accelerate, give energy to a particle using the magnet. A magnet, because a magnet, the force is perpendicular to the motion of the particle, and so essentially will have zero, will make no net work on this. And so in this case, you have just to use the magnet just to keep the particle on a trajectory and use the electric field to accelerate it. And so all the history of accelerator has been developed in two ways. If you go back to the previous slide, you see that the first thing you say, I make a very huge electric field and static field, and then if I inject in there a particle, this will accelerate. And of course, these were the first accelerator which were done. Start from the very simple one, the cathode ray tube. You are all too young just to remember cathode ray tube TV, but this was a very common accelerator which was in everybody's house, because essentially a television was using a cathode ray tube just to paint on the screen, on the phosphors of your screen, an electron beam which was giving you the images. The electrostatic accelerator became smarter and smarter in the beginning of last century, and they reached their maximum development around the 30s. There are still some of them around. Maybe that in your virtual tour you can be shown one of them, which is still in the laboratory of Frascati. And then the other is the one in which people understood that was much more efficient and was not buying so many problems, just to have an electric field which was varying in a smart way. So you were using it only when it was needed, and you were avoiding just having a static field have a problem that after a certain voltage, they start provoking these charges. So the first accelerator, they were used even before being discovered, because when in 1895, more than 120 years ago, Röntgen discovered the X-rays using a cathode ray tube, and made this beautiful picture of the hand of his wife carrying a ring. It was not totally understanding what he was doing. And as a matter of fact, he didn't understand that one of the things which were provoking this emission of X-rays were electrons. And was Thomson that a couple of years later, just trying just to understand the mechanism, discovered that if you put a magnet near the cathode ray tube, you see that the spot moves, and he measured the charge of this electrical particle going around, and discovered that these were the electrons. And this was the first discovery that was done with an accelerator, if you like. And he could not understand why he was making a comment. He could not understand why these particles, which were so tiny, so useless in a sense, were doing so much. And electrostatic accelerator, more sophisticated than that, are used also nowadays as sources for making the initial part of the beams that we are using in the bigger accelerator. Another way was just to increase this voltage that was at the limitation in a glass tube. And this was first bright idea was this Cockcroft-Walton scheme, in which Cockcroft and Walton in 1932 they invented this generator, which was essentially at every step increasing the voltage gap. And with that, they succeeded just to make the first artificial breaking of an atom. They took protons, they were shooting it against lithium atom, and they were producing 2 helium atoms. This was the first transmutation ever tried. There was then the evolution of this to the Van der Graaf accelerator. Van der Graaf accelerator is even another smart thing. Imagine that you have a belt, like here, which is rotating, and you have something which is like when you caress your cat. You start transferring electric charge. This electric charge goes up with this belt, which was a rubber belt, and then you have electrodes which pick it up, and they load all this sphere which is up there. So an enormous field by accumulation is made here. And then if you inject a particle here, this will be shot down by the field which is in there. Of course, there is a limit you can do that, because when you exceed a certain amount of voltage difference, you'll have a discharge. And in 1933, this limit was around a few million volts, which was a big achievement. You can do Van der Graaf nowadays with better materials at 20 million volts. But the real changing of the thing when people understood that if we're using a radio frequency, they could essentially gain in efficiency enormously, and get to accelerating particle very efficiently in a very short distance. Because you can imagine these Van der Graaf were getting taller and taller and bigger and bigger, and still they were only accelerating to 7 MeV, mega electron volt, with very tall structure. Now you can make with radio frequency up to 100 million MeV per meter if you put a particle in there, after 1 meter, it will be accelerated to 100 MeV. And the idea was just to have use the principle of the surfer. The surfer gets on the right phase of a wave and lets the wave transport him for a long time. The problem is that you have just to create something which makes the surfer stay in the right place, because if he goes instead here, if he's accelerated here, he will be decelerated when he is here. And this at the beginning was done in a very smart way, because people understood that, for instance, they could accelerate the particle when there was the right phase, the field was in the right direction, and then shield the particle, having it go inside a shielded volume, for instance, in a metal tube, where it was not feeling the wrong phase, and so on, in such a way that at the end you had a net acceleration, because you were shielding it from the wrong phase electric field. And this was refined. The initial scheme, because this scheme was suffering from the fact that at high frequency, you essentially the field was not staying where it was, but it was spilling out, making it very inefficient and giving origin to breakdown. So enclosing this radio frequency in metal boxes, making these pill boxes, as they were called, and making one after the other, nowadays we can make gradients which are very high. And the first one, which was a big success in the 50s, was started at the end of the 50s and was completed in the mid of the 60s, was a 2 mile long, 3 kilometer long accelerator at Stanford, which survived and made a lot of physics for many, many years. And the linear accelerator are going on, and now there is the design, there are designed for a 30 kilometer long linear accelerator. And linear or circular is depending on what particle you accelerate, because if you are accelerating particle which when go round they lose a lot of energy, at some point it will not be convenient, because all the energy you are giving for acceleration will the particle, before coming back just to get the next amount of energy to keep accelerating, they will spit it out. And so you will end up either with making a machine which have a much longer radius, a much bigger radius, which is not convenient, or otherwise you'll have just to go linear, because when you go linear, this emission of synchrotron radiation is much, much reduced. And the idea just to make this accelerator of a certain diameter came up when people understood the dynamics and the optics which was inside an accelerator. And instead of having this particle essentially spiral until they were going out in a cyclotron like here, they made it in such a way that while the particle were accelerating, they were raising the magnetic field in such a way that the particle were staying always in the same orbit inside a confined optics. And this started what nowadays are the machine, or the circular machine around the world are essentially the big one are all synchrotron. Circular accelerator, as Catarina said before, are of many sorts, and some of them are specialized because they don't accelerate only a beam, and they throw it against a target, but they accelerate a beam, two beams, which are counter-rotating. And this is because it's more efficient, it's much more efficient. As you know, when you accelerate a particle in relativity, the particle, since it has a mass and it cannot exceed the speed of light, it gets more and more mass. So essentially, you're starting, imagine that you're starting from two tennis balls. And in normal life, in classical physics, if you throw a tennis ball against another tennis ball, and you throw it at 100 kilometers an hour, and the other is at rest, the energy in the heat is essentially the one which is given by the one. Is equal to the fact that if you get one at 50 kilometers an hour against another one at 50 kilometers in an hour, because it's simply a change of a reference frame, is the same phenomenon. But imagine that in relativity, when you are starting giving momentum to a particle, the more momentum it gets, and the bigger this ball becomes. And if you accelerate it enough, you make it as big as a tanker. Then in this case, it's much more efficient just to accelerate both of them, because you make a tanker against another tanker instead of a tanker against a tennis ball. And that's why we are making colliders. The technology is constantly evolving. We have learned now just to make stronger magnets, so we can keep in a close orbit at higher energy particles. We have, for instance, used thousands of superconducting high field magnets in LHC, in the machine at CERN. And we are thinking how just to make more efficient way in which we can accelerate particles. And one of the things which is being studied in Frascati, for instance, now, and not only in Frascati, is the acceleration in which you create a plasma wave, essentially shooting high intensity laser inside some dielectric material. And this plasma waves is structuring itself, and it acts like a radio frequency of very high field. And so essentially what was before 100 megavolt per meter could become 100 gigavolt per meter. And there are already very interesting experiments done in this sense. So this is a brief overview of all the particle accelerator. Elementary particles in the 19th century, they started from very far away. They had the table, the elemental table. They knew essentially already a number of things, and they could infer, for instance, by using simple numbers, the Avogadro number, the density of the thing. So they knew more or less how the atom, how big the atom should be. And so an atom should be an object of the order of 10 to the minus 8 centimeters. Then when Thomson discovered the electron, essentially by moving with the magnet, and measured that the mass of the electrons was very close to 1 part over 2,000 of the mass of the hydrogen. He could the model that he had in mind was, well, this massless particle should be like the seed or the candies inside a cake. And so essentially his idea of an atom was a sort of thing of which was electrically charged, and then it had inside negative charges, which were essentially making it globally neutral. Of course, experiments proved that this was wrong, and Rutherford, which who wanted just to study this model, should use the first artificial beam of particle, which was obtained essentially using alpha particle. Alpha particle are nuclei of helium atoms, which are spontaneously emitted by radioactive isotopes at a speed which is of the order of 5% of the speed of light, but they are heavy because they're helium atoms, so they have a large mass. So for the reason we said before, even if the speed is small, their momentum is pretty high because the mass is high, so their wavelength is small. And so what he observed is that these alpha particles were deflected at a very high angle, and which was not expected if you had the Thomson model, because in this case, on average, you will be deflected 1 bit one direction, 1 bit in the other direction, and then the deflection will be close to zero. And Rutherford himself was so incredibly astonished, because he said, if you are firing a cannon shell against a foil of paper, and you see the shell bouncing back, because sometimes when you hit the nucleus. And what is was his conclusion is that the atom was essentially done by something which was very dense and very small, of the order of 10 to the minus 13 centimeter, which was containing all the positive charge, and then it was surrounded by a cloud of electrons. And you can imagine, from 10 to the minus 8 to 10 to the minus 13, there are 5 orders of magnitude. So means that on average, an atom is empty. And if you come back now and you remember the principle of the de Broglie, you see that in this case, already with this very low energy for nowadays standards alpha particle, if you do the very easy calculation there, you see that it could resolve already at the level of a few 10 to the minus 13 centimeter. There were a lot of wrong ideas before 1932, because, for instance, the mass value of light nuclei should be a multiple of the proton mass, but some of these hypotheses essentially were not coming to the thing, because there were atoms in which you could measure their atomic number and their atomic mass, and essentially the only explanation that you could have is that you were finding something which was double as much as the charge that you were measuring. So the first explanation which was given is that the atom was done by protons, and double as much as needed, and half of them was essentially nullified by electrons which were inside. The problem is that the spin of nitrogen, which is a very common atom, is an integer number. And since the atomic number of the number is 7, if you make 7 protons, 7 other 7 protons, and 7 electrons, you end up, and since they are all spin 1/2 particle, you could not come to the thing. Of course, the explanation was different. There was another particle, which was the other particle, which was discovered. Now, in this moment, we have essentially discovered only electrons, protons, and photons. The next particle which was discovered was the neutron. And the neutron was discovered by Chadwick in 1932 with a very smart experiment in which, again, using alpha particle and putting it on a target, he was capable of measuring with a cloud chamber, which was a very easy, a very rudimentary object, but very smart, in which you had a super saturated gas, in which when supercritical gas, when vapor, when a particle was coming in, was making the seeds of small droplets, and then you could take a picture of that and measure it. And if you put in a magnetic field, you could measure the curvature and measure the kinematics. And he discovered by inferring the thing that exactly this was there was a particle which was neutral and which had almost the same mass as the proton. And this solved the problem. The other problem, which immediately came out in these fantastic years in which people were increasing their knowledge of the fundamental constituents in an exponential way, a theorist studying the evolution of the behavior of an electron in treated in a relativistic way in an electromagnetic field, he discovered that his equation, the famous Dirac equation, had two solutions, one with positive energy and one with negative energy. And he was courageous enough just to infer that the negative energy state describes the antiparticle of an electron. The antiparticle is a particle which has the same mass, opposite charge, and if it meets with his sibling, will dissolve into energy. And you bet that after not very long, essentially 1 year later, Anderson found it in the, and he found it in a smart way, because if you have a particle in a cloud chamber and it curves, if you don't know in which direction it goes, you will never be able just to tell whether it is positive charge going this way or a negative charge going the other way. But if you put a piece of lead in the middle of your chamber, you'll know, because in this case, a particle which goes this way will lose energy. And so its curvature will increase because you will have lost energy inside the lead. Just to make a long story short, this was the confirmation of the existence of a particle which was ionizing like an electron, which had the opposite charge of an electron, and which was the other particle which came immediately to the attention of the people was the neutrino. And the neutrino has a funny story, because people knew that about radioactive decays, and in principle, if a body decays in two bodies, once you measure one of the two bodies, the energy of the other one is perfectly known, and so you should expect a fixed number. But this was not the case, and the spectrum of the beta particle emitted by radium was essentially continuing going up to the point where you should expect just to have it. And Pauli, there were several wild attempts to explain it, including there were very famous physicists who thought that the principle of conservation of momentum and energy was essentially violated in atomic physics. Pauli was the one that attempted on a pure speculative way just to give an explanation. Say, well, imagine that there is a particle which is a spin 1/2 particle, has very small mass and is neutral. Then this is three-body decay, and then everything is okay. And in principle, this could work. But he says, I have done a terrible thing. I invented a particle which probably doesn't exist, and if it exists, it cannot be seen. Of course, and he called it neutron because at that time the result of Chadwick was not out. It's Fermi that called it neutrino and gave it a very elegant theory, which was the beginning of the weak interaction theory, and gave it a very elegant theory of how this neutrino postulated neutrino, and gave it not only the name. And this is also another very nice thing, because he took the same formalism of that people were using in quantum mechanics just to describe a different phenomenon, which was this weak interaction. And still nowadays, the coupling constant that we are using, like the one that we are using for gravity, or for electromagnetic interaction, or for strong interaction, is called the Fermi coupling constant. And neutrino, of course, have a very weak capability, probability to interact with matter. If you imagine that a neutrino can travel across the Earth 1,000 times without interacting, means that if you want just to see a neutrino interaction, you have just to make a lot of them in such a way that at least one interacts. And this was done at the beginning. To discover neutrino was done using reactors. Reactors produce a lot of neutrino. If you imagine the sun is producing about 10 to the 38 neutrino a second. On your thumb, in this moment, you have about 10 billion neutrino, solar neutrino going across them. And of course, since they are neutrino, they are not interacting very much. And the first experiment who was capable of looking at the neutrino, which are produced in fission reactor, which was in Savannah, was this experiment in 1953. At the same time, people had discovered that there are accelerators, and nowadays we know that these accelerators are much stronger than any accelerator that we will ever be able to build, because people started observing radiation coming from the cosmos, very high energy radiation, which was containing particles which were not produced on the Earth. And this is how the people observed the muon, and not only the muon, and the first pion. So at the mid-60s, people started just to have an idea, more or less, of what was going on. And what was going on is that people understood that there were 4 types of interaction. One, which was the gravitational interaction. Then there was the weak interaction, which involves all the particles except the photons. The photons have zero mass, so they don't feel electromagnetic interaction, and strong interaction. And just to give you an idea, we are very subject, very to the gravitational interaction. But if you look at the strength, the coupling constant of the gravitational interaction, this coupling constant, this G that is in front of it, is 40 order of magnitude smaller than the one of the electromagnetic interaction. So in particle physics, we totally neglect the effect of gravity because it is unmeasurable from this point of view. And there is another important thing that people have understood in this year, is that in quantum mechanics, there are no static field of forces. Forces are always mediated, transmitted by intermediate particles, which act as interaction carriers. So the photon is the carrier of the electromagnetic interaction, and other carriers like the intermediate boson for the weak interaction, the gluons for the strong interaction, and so on. And these particles are, in a sense, for instance, the photon, which carries the interaction between particles, is not a real photon because it has a mass which is different from zero, because it can have a mass different from zero for a short enough time, obeying following the uncertainty principle, which was stated by Heisenberg at the beginning of the last century. Mediators of this particle were also, if you have a strong interaction is the interaction which keeps a nucleus together, because if you imagine that a nucleus is made by neutrons and protons. Neutrons have no charge. Protons have all positive charge. So in principle, they should fly apart, unless there is an interaction which is stronger than the electromagnetic interaction, which keeps them together. But this interaction, this strong interaction, should not extend very much out of the nucleus, because otherwise it would crush all the atoms and all the matter around it. So by knowing that the nucleus is 10 to the minus 13 centimeter and knowing that the force should be acting inside there, Yukawa postulated the existence of the pions, which was discovered not after a while. And by the fact that protons were very stable, and the people started looking with accelerator at all possible reaction, they started seeing that there were conserved quantum numbers, like the conservation of quantum numbers that you have in atomic physics. And more of these were coming up because people, for instance, at some point found a type of particles which had peculiar behavior, because they were only in particles, and then later on we'll see what was this strangeness coming from. The other thing which was not clear at that time was that we knew that electrons had their antimatter particle, but was not clear whether particles which were like protons or neutrons had an antiparticle themselves. And again, with another accelerator, they discovered antiproton when they succeeded just to make an accelerator which was strong enough just to produce them. And this was done when the first accelerator reached the 6 GeV energy. And surprises were still piling up, because they discovered that the neutrino, which was there, was not alone. There was he had another brother, which was different from him, and this essentially was done again with an experiment in which they were producing a lot of muons, absorbing them in such a way that they decay, and then they were measuring the neutrino, which was the only thing which could come out of these absorbers, which were meters of steel, was the neutrino. And they discovered that most of these tracks were essentially compatible, that they were producing a muon. So this was a muon neutrino, and only a few of them, which there were a contamination in the beam, were electron-like neutrino. And this granted the Nobel Prize. So at the end of the 60s, and mid-60s, people were essentially in trouble, because there was a zoo of particles, and nobody could believe that all these particles were fundamental. It was confusing. People started seeing regularity. There were a lot of models which were discussing this and that. But at the end, there was a very good grounds to think that most of these particles were not fundamental. They were composite particles of something which was more fundamental. And one of them is that it was clear that these particles were not point-like. And this, for instance, was done looking at their magnetic momentum, which was, in case that they would have been point-like particle, would have been a number of Bohr magneton, and in this case was measured totally different from that. So there was a brilliant idea, which at the beginning was essentially an idea which was a pure mathematical thing, trying just to exploit the symmetries that these particles were showing, and was essentially the assumption that you could build all this zoo by using three constituents, which they were called quark by Murray-Gell-Mann, and one of them was called up, the other one was called down, and the other one was called strange. This quark had a fractional charge, and by up at plus 2/3, down minus 1/3, strange minus 13. And of course, the three quarks had also their own three antiquarks. And with that, you could build all the possible particles you had observed so far, and even predict one of them, which was this omega minus, which was essentially the assembly of three strange quarks. And essentially, this particle was predicted and was found a few years later. It is a very rare particle just to make, especially with the technologies and the accelerator of that time. And of course, there was a problem that people say, well, but this cannot be real, because if you put three quarks together, since they have a half integer spin, their wave function, the global wave function, should be antisymmetric, because they are fermions. They should obey Pauli principle. And instead, if you put simply these three SSS together, you end up with a symmetric wave function. And this was
Sergio, sorry,
yes,
can you resume?
yes, and I will okay. Can you hear me?
Yes, we hear you.
Okay, so essentially, this construction evolved because in not a long time, this static model was proven by experiment that the quarks were particles which had the physical meaning, although you could not see them free because they interact in such a way that they cannot come apart, because every time they come apart, they form a couple of quark and antiquark. And this gives origin to real hadrons. And this was done by the introduction of the particle which brings the strong interaction, which is the gluon, which comes with three charges that we call colors. The last thing that we had just to discover was the Higgs boson, and this was done at LHC not long ago, because the Higgs boson is the particle which in the standard model is responsible just to give the mass to all the constituents. And the boson, the Higgs boson, was found at the end at the LHC in 2012 with a gigantic effort, which brought to the discovery of the Higgs boson and to the production of the properties of the Higgs boson to determine that this particle was exactly, unfortunately, the Higgs boson proposed by the standard model. Now, we know that the standard model now is complete, but it does not explain all the things that we would like to explain. It doesn't explain dark matter. It does not explain dark energy. It does not explain why in this universe there is an overabundance. We see this universe is done by matter, and at the beginning should have been done by the same amount of matter and antimatter. So essentially, there are many, many things that we have still to look at and discover. And most of these things, many of these things, will need accelerators. Other accelerators for neutrinos, for instance, for pushing up the energy. But they will have just to work together with other type of experiment in the space, looking at gravitational waves, looking at precision measurement that can be done at lower energy, but with other, and by essentially looking at unknown unknowns, because it's clear that the standard model is very powerful. We have not succeeded so far just to invalidate it, but we know also that is not complete. And so essentially is a lot of fun for all the younger people, which in the next year will be doing this type of research. Thank you.
Thank you very much, Sergio. So we have had an overview of what has been happening in practically even more than 100 years. So end of 1900s, end of 19th century up to now. And so I want to, I see already a question. Why are there 3 generations of matter from Donatella?
Well, there are 3 generations of quarks because the first 2 generations, which were discovered, up, down, strange, And then there was a fourth one, which was the charm particle, which was discovered in 1974, which was a fourth quark. If you have only 4 quarks, you cannot explain why matter particle behave in a certain way. For instance, they violate one of a symmetry, which is the symmetry of the mirror and the symmetry of the charge conjugation, which connects particle and antiparticle. So it was inferred that maybe there is another generation of quarks. And at the same time, we knew already at that time that there were 3 generations of leptons, because there was the electron, the muon, and the tau lepton, which is a very oversized lepton, which has a bigger mass than the muon. And people started just to look at them, and they found essentially the B quark, the beauty quark, and the top quark in the 90s, the last one. And that's has completed this sort of scenario. Of course, we are still looking if there are more of them, but in the standard model, these are enough just to explain everything. Of course, if there are other type of particle of interaction, there could be more constituents.
Yeah, so other questions, guys, come on, ask questions. That's your chance now to ask questions. So, but basically, we don't really know why 3 and not 2 or 4.
No,
or
we know we know why not 2, because with 2 you cannot have CP violation, and so there should be at least 3, because you must have just to explain what we see, for instance, from the decay of the kaons at Daphne, there should be at least 3 generations, but could be 4, could be. So far, we didn't find any evidence for that. But the most striking thing that we don't, in my opinion, is we don't understand is this thing. I mean, this is a logarithmic scale. So you go from the mass of neutrino, which is much less than an electron volt, you go to the top quark, which is a fundamental particle, but it has 180 times the mass of a proton.
So it's like nearly like a gold, like
yes.
gold.
And so essentially, you don't understand why the nature has needed just to, what is the dynamic origin of the mass? This is the question. Why, in order just to keep this world together, and you cannot take away the top or the bottom, any of these particles, or the Higgs, because otherwise the standard model fails. But not only fails the standard model, the phenomena that we are measuring would not happen. So they are fundamental for explaining the experimental results. But we don't understand why there is this hierarchy of mass, which is enormous.
Sure. So I see from Lorenzo, he's saying that they are speechless because of all this beautiful information.
Well, I had even more, but I leave it to them in the slides.
Now let me ask you, if you would have unlimited money, what accelerator would you build?
I would not build an accelerator now. Probably if I had unlimited money, I would try just to build an accelerator which now is difficult just to imagine, which is instead of accelerating electron or protons, which are the matter that we are accelerating now, I would try just to accelerate muons, just to make very precise measurement of the thing, because we don't know now what is the next scale of energy which makes sense. When we built the LHC, we knew that the LHC would have either found the Higgs boson or destroyed the Standard Model. And there was one who was hoping not to find the Higgs boson, but to prove that the Higgs boson was not existing, which is different than not finding it.
Yeah, let me remind that the Higgs boson was found when you were the CERN scientific director.
Yeah. I mean, I was a lucky guy, and just to be, I am specialized in fat particle. I also was in the experiment to discover the top quark, and but in principle, now we don't have. We can explore another energy, but it's just like going without no map at all. Now, with the Higgs, we have finished what we were calling before all the known unknowns. Now we have just to explore the unknown unknowns, but at least before just adventuring in some place, because the next accelerator, if we build it bigger, will cost a lot of money, which is a problem, but it will cost also the work and the future of a lot of scientists. Suppose that you work for the next 20 years and on the wrong assumption, is not very smart.
Let me try to select some other question. We have 3 more minutes. So there is one question related with quantum physics. Keep that one, Valerie. Keep that question. We will have a dedicated talk on quantum. So that one is specific to that talk. There is also a question from Chiara. What could be the applications in the daily life? Keep it for tomorrow. There is one of these applications which is being brought to you. What can be done with accelerators? Instead, I see one question which it's asking is if there is any other model that could be true other than the standard one, from Danilo Lipac.
Well, there are models which are trying just to be, for instance, supersymmetry was the model which was very fashionable when which could have give a good explanation of dark matter, good explanation of the mass of the Higgs boson, because the mass of the Higgs boson in the Standard Model is too small in a sense, which was essentially giving supersymmetry was an extension, was the symmetry between. You have seen in this picture, there are the constituents, the matter particle on this side, and there are the force carrier particles on this side. So the photon, the W boson, the gluon, and the Z boson, which Z and W carry are heavy photons, carry the weak force. The supersymmetry was a stronger, a more complete theory, which was making a symmetry between the matter particle and the force carrier particles, and which would have given origin to every particle in our world would have had a partner in the other world. All the fermions had a partner which was a boson, and all the boson had a partner which was a fermion. It would have been a fantastic bonanza for all the particle physicists, because it would have populated another big zoo. And supersymmetry is a sub-theory of the string theory. The problem with supersymmetry is that we have not found supersymmetric particles so far, and we are still looking at them, but up to a mass very close to 1 TeV, which means 1,000 times the mass of a proton, we didn't find any of them. And we are still looking at them, of course, and NEC is still looking at them at higher and higher sensitivity and energy. The other problem is that of string theory, which again is another very powerful theory, because it substitutes the idea, it has a different perception of what reality is, in the sense that it substitutes point-like particles or filled with extended fields. It has not yet a predictive power which can be tested experimentally.
Thank you very much. Yeah, we reached the end of this talk. It was very, very interesting, and I thank you once again. And well, I remind to you who are listening to us that there is another talk starting in about 20 minutes, so at 4:40 Italy time, which is centered on a detail of how actually an accelerator works. So we will have a person who works and designs accelerator, who will show us how an accelerator people work and what it's exactly doing in order to be able then to arrive to produce processes which are then bringing us to this knowledge about the world of particles, what we know today, and why not maybe tomorrow to discover something related to what stays beyond the standard model, as we have heard now in the very last minutes, and to discover new things for which Dr. Bertolucci was inviting you to join this adventure in the near future. Good. So thank you very much once again, Sergio Bertolucci.
Thank you all.
Being with us this afternoon. And to you who are now listening, we are awaiting you back in less than 20 minutes. Just be with us. Let us know again where are you coming from and who are you, and join us for the accelerator, how we will accelerate you in the accelerator world. Thank you very much.